Hello, this is Unlock Circuits 18EC 42, corresponding to the Module 3, Lecture 1, Part 6. We are discussing the exercise in this video for the shunt series feedback topology. So the example is find the current gain I out by I in, the input resistance R in and the output resistance R out. The transistor has beta equal to 100 and VA equal to 75. So now this is the given circuit to us, and because we have an emitter, what you call okay, this is a bypassed emitter resistance, so this is a so to say biasing circuit for this transistor. So naturally this is not going to come into picture when we do the AC analysis because of the bypass over here, and the DC analysis has to be done with respect to the what you call um, voltage divider bias circuit over here. So this transistor can be replaced easily by the model which is the hybrid pi module over here. However, this can be replaced by either this model depending upon the need, and or preferably this model, because of the reason that this consists of, this is having an emitter resistance over here. So this is a common emitter amplifier with source emitter resistance, common emitter model with the emitter resistance which is RE2. So now doing the DC analysis for this, so this RF corresponds to the feedback resistance over here. So, and that will give you the feedback network. So DC analysis for this is by neglecting the beta and VA will be VB1. How do we find the voltage at the base? Here, that will be, you have VCC here. VCC multiplied by RB2 divided by RB1 plus RB2 is the one which we have written over here. 12 multiplied by 15 divided by 15 plus 100. That is the value which we have written here. Or otherwise, you can say that the current flowing through this is the 12 divided by 100 plus 15 will be the current. That current multiplied by 15 kilo ohms will give me the value of the voltage at this point, which will be equal to 1.57 volts here. So once having found this, then the voltage at this point is this voltage minus this voltage. So the voltage here is 1.57. The voltage between VBE will be, when it is in the active region, will be 0.7. So 1.57 minus 0.7 will be 0.87 volts. So biasing is done such that this operates in the active region, and when active region is there, VBE active will be the value 0.7, and hence we'll get 0.87. IE1 will be the value of the current which is flowing through this at the time of DC, and the value is 870 ohms, so 0.87 by 0.87 will be equal to 1 milliampere. So 870 will give us the value 0.87 kilo ohms, and that's why this will become 1 milliampere. So having found this, then the VC1 is the voltage which we can find here, which will be the value which just corresponds to the 12 minus RC1 into IC. 12 minus RC1 into IC. So 12 minus 10 into the value of, so when IE1 is equal to 1 milliampere, we can approximate IC also to be 1 milliampere, neglecting the base current over here, So we are just taking 1 milliampere value itself as the collector current value, and thus we'll get 2 volts here. So having found the voltage here, then the what you call, so you have 2 volts here, 2 minus again 0.7, 2 minus again 0.7 will give me the 1.3 volts as the emitter voltage of the Q2, VE2. So having found this, again we can find the emitter current, which is 1.3 by 3.4 kilo ohms here, and that turns out to be 0.4 milliamperes. So 0.4 milliamperes, and we can consider again that that is the current which is, over here, by neglecting the current which is flowing here. So IE is considered approximately equal to IC. So 12 minus 8 into IC2, which is considered same as IE2, is like this: 12 minus 0.4 into 8, that will give us 8.8 volts at this place. 8.8 volts at this place at the DC. That means when we have not given any input voltage, when we are not giving any input voltage, the voltage here is 8.8 volts. So now we need to do the analysis. What we are trying to do over here is, the equivalent circuit RS, and then this value will be naturally in the analysis. These two, this will go to ground, and therefore this will become parallel with each other, and then this is replaced by the what you call model over here, and that's why we are going to get this thing R pi 1, and then GM 1 V pi 1. Voltage across the R pi 1 is V pi 1, and then RC1 is there in parallel with it. This RC1, again, this is going to go to ground, and RC1 will come. And this can again be replaced by the same type of model, or better is you can replace it by this. But we have written here the, what you call, in this figure, the pi model only is written. You can replace it with, depending upon the analysis, we'll discuss that it's better that this particular, block, this particular block over here can be replaced by the model here, okay? Or we'll see when to use this and when to use this. So having done that, now on this side, this RF is taken out, so this RF and RE2 are going to come in series. The rest of the thing is same. On the output side, we'll have this same, and the value of R pi 2 will be as it is, and we are taking out this here, and then these two will become in parallel. Rather, when we are trying to find the output side, then this source should be open circuited, so RF should come in series with the parallel combination of all these three. But might be the parallel combination of all these three is much less than the value of RF, hence that might have been neglected in the circuit. So let us consider that this is grounded, and hence only we are having RF, which is in parallel with RE2. So having found this, now this is the what you call rest of the equivalent circuit, and we'll have the RC2 in parallel with RL over here. Rout is the resistance which is found here. Rin is the resistance which is found here. Rin with parallel with the RS will give us the value of Ri. So the input side analysis can be done like this. Ri, the value of Ri over here is the parallel resistance of all these together. So the value of V pi 1 will be II into the parallel combination of all these. And that is what is mentioned here. V pi 1 is equal to II dash, and RS in parallel with RE2 plus RF in parallel with RB in parallel with R pi 1. So this is the equation to find V pi 1. Having found V pi 1, then we can find the value of VB2 here. VB2 is the voltage here, and that voltage is the current here will go in the reverse way. So minus GM V pi 1 will be the current which will be there in flowing through the parallel combination of RO1, RC1, and then another parallel one which will correspond to R pi 2 in series with the parallel combination of these two. Now, this is rather the current which is flowing through this network is the IE current, but this should be translated onto the base side to add to the R pi 2. So therefore, first two parts you can see RO1, RC1 here parallel, but the rest of the thing is R pi 2. This translated onto the input side will give us translated onto the input or the base side will give us that RF in parallel with RE2 has to be multiplied by beta plus 1, and that should be added to R by 2. So, and that is what we have here, beta plus 1 in parallel with RE2 in parallel in RE2 in parallel with RF multiplied by beta plus 1 plus R by 2. That is the total, equivalent of this by translating this from the emitter side to the, base side. So, having written that, the value of the I naught dash, the I naught dash is the current over here, and that will be the voltage here. The voltage here can be considered. I can now replace this by this equivalent circuit. This whole thing can be replaced by this equivalent circuit now. So at that time, we are left with, here we will have a RE, right? This base is this point, and then we have RE, and then we have the parallel combination over here. So VB divided by RE2 plus RE2 in parallel with RF is the value which we'll have here if we replace this total, pi model by means of the T model over here, RE in series with the parallel combination. These two multiplied by the value of I naught dash will be equal to VB2, or otherwise IO dash I naught dash will be equal to VB divided by the RE plus the parallel combination of these two. That is what is written over here. So then A is equal to I naught dash by II dash. I naught dash is there here, and in place of VB2 we can replace this, and then II dash can be written from here, V pi divided by this. So overall you can substitute all the values given there, because the value of V pi 1 will cancel, and then substituting in that we are going to get minus 201.45 amperes per ampere, because it's current gain. To find the value of beta, the input side, the feedback current, feedback point rather should be connected to ground, and we have RF and RE2, and I naught dash will be the sum of the currents which are flowing through this, current like this and current like this. Now this current and this current are reverse, so therefore the IF dash will be minus of the current in the opposite, the other arm, RE2, divided by the resistance in the opposite arm divided by the sum of the resistors. So minus of RE2 divided by RE2 plus RF. The current which is flowing like this will be I naught dash multiplied by RE dash divided by RF plus RE2. The current which is flowing like this, which is IF dash, will be minus of that. That is why we have this, and hence we will be having this value. Then we need to find the input and output impedances. Input impedance is a straightforward one, which is whatever we have, written over here. This is the input impedance itself, because V pi 1 is itself the input value over there. So this becomes the input impedance. That is what we have here. Okay, same thing is written there, 1.535 kilo ohm. RIF will be RI plus 1 plus A beta. A we have found, beta also we have found. Substitute that, you'll get 29.5 ohms. Rn will be, we have written the formula, 1 by RF minus 1 by RS, and 1 by RIF is this value, 1 by RS is given to us, and we can substitute and we'll get 29.5 ohms. Then the output side, RO, you can try to find out RO. RO can be considered from the circuit over here. This is the value of RO. The value of RO which we need to find from here, and that value will be the value which corresponds to RE2 in parallel with RF. RE2 in parallel with RF. RE2 in parallel with RF. The RO is the value where do we have RO? This is RO. So RO can be considered as the resistance which is measured at this point, and corresponding to that, we have here RE, and RE again in series with the parallel combination of these two. RE2 is this value, and then the series combination in series with the parallel combination of these two, RE plus RF in parallel with RE2, and then on this side it will be the RC1. RC1, you can consider this as a open over here, RC1 in parallel with RO1, these two together, okay, because we are totally replacing this by this. So RC1 in parallel with RO1, but this is on to the base side. We want it on to the emitter side. So therefore, this quantity has to be divided by beta plus 1. And that is what we have here. That is what we have here, RC1 in parallel with RO1 divided by beta plus 1, and this total quantity here. So if you substitute these values, you will get 2.69. ROF is equal to R0 into 1 plus A beta. That is, again, you need to multiply R0 with this value. Then Rout is the resistance which is measured here. So for that, we can just consider the equivalent circuit like this, where we have ROF here, and Rout is the resistance which is measured from here. For this, we can put the, again, this can be replaced by the model, something like this. This is the model we can write over here, where we can write ROF there at the proper place, and this is just the model which is we are going to put here by putting a voltage source Vx over here, and then the input side is grounded. So then you can write the equations. The total analysis for this will be something like this. For this transistor, you can try to write the value of V by R pi. This current plus this current will be equal to this current. This current plus this current is equal to this current. So therefore, this current will be equal to V by R pi is a current, will be equal to this current minus this. So effectively, it will be 1 by R pi is equal to 1 by Re minus Gm. 1 by R pi is equal to 1 by Re minus Gm. That's the first equation which we'll get. And then, so having written that over here, that is the one which is derived here, and having written that over here, then we go for the next one, that is at the node E. The node E, if you see there in the figure, at the emitter, we have here this current plus this current is equal to this. So that is V by ROF is plus V by RE is equal to IX plus GMV. And that's what is mentioned there. If you, what you call, write that over here, simplify it, you'll get IX is equal to 1 by RE plus 1 by ROF minus GM into V. 1 by RE minus GM here is 1 by R pi. So thus we'll get Ix is equal to 1 by R pi plus 1 by ROF into V. And this is nothing but the inverse of the parallel combination of R pi and ROF. So therefore, we can write V by R pi in parallel with ROF. Also, we can try to write the equation for Vx. That is, this Vx is nothing but the voltage across this and the voltage V. The voltage across this and the voltage V. And that is what is mentioned there. So, however, this V is very small. It can be neglected here itself, or you can write this and neglect it. So, Ix plus GMV, V, we can just write from here. So, that's nothing but Ix into R pi in parallel with ROF. That is what we have written here. V again can be written as Vx Ix into R pi in parallel with ROF. So this is very small. You can neglect here itself or here, whatever it is. So we are left only with this. So we'll get Ix common, you can take out, and Vx by Ix will be the R out value, which will be this, which we have written there. 1 plus Gm R pi in parallel with ROF. And that is the formula which is written over here. And we are just substituting the different values and getting the value 18.1 megaohm. I out by I in is I out by Is, that is equal to the value which is, RC2 divided by RL plus RC2 multiplied by IC into Is. So this will be the at the output side. If you go back to the what you call over here, this one, right? So this is RC2, and this is going to go down to the ground, and hence we can try to write corresponding to that the equation. So I out will be nothing but the value which is RC2 divided by RL plus RC2, that is current within the load. I out the current within the load RL is RC2 divided by RL plus RC2 into IC divided by Is, and IC itself is I0, and we are going to get the different values substituted there. That will give us 3.44 amperes per ampere. So this finishes the numerical.